Welcome. Today I'm going to talk about graphs of multivariable functions. We're going to understand notation for multivariable functions. I also want you to be able to find the domain of multivariable functions. As far as graphing multivariable functions, we're going to look at vertical traces, horizontal traces, and we're also going to construct contour plots. We're also going to calculate average rate of change based on a contour plot and steepest ascent based on a contour plot. Finally, we're going to understand and graph level surfaces with just a limited example. I'm going to talk about all of this stuff here at the board. One of the parts of this video is going to be looking at using three-dimensional graphing technology to be able to visualize these in a way that you can't do just looking at this flat surface. So what is a multivariable function? A multivariable function is a function whose domain values are n tuples. What does that mean? It means typically we talk about ordered pairs. Instead of ordered pairs, we could have ordered triples or ordered quadruples if we had 4 different inputs. And an n-tuple is one that has n inputs. And we're thinking of this, you can visualize this as a point in Rn. Meaning if I had n-dimensional space, this would be a point in Rn. And our output values, our range values, are real valued numbers. So they're just a single number as a real valued number. This definition might not be very helpful. Let's look at an example. So I'm going to give an example of a multivariable function that has 3 variables as the input. So I'm going to call those, instead of x1, x2, and x3, I'm going to use the convention that typically if you only have 3, they're going to be x, y, and z. I could equally label them some other variable name if I felt like labeling them a, b, and c, for example. And let's look at a function that's given by maybe square root of x minus 3y all over 2 minus z. So notice that the inputs into this function are ordered triples. So we're thinking of the domain values as a subset of R3. But we have to be a little careful. Because not any element in R3 would work. So my inputs, or domain values, are points in R3. But I have to be careful. I notice here that I have a square root over my x, and square roots can't be negative. So I know that my x values have to be greater than or equal to 0. That's something that could go wrong in the domain of this function. That negative x values don't make sense for the domain of this function. It looks like my y values can be any value that I want. But here I also have to be careful that I can't have a denominator equal to 0. So I know that I need to make my 2 minus z not equal to 0, or in other words, z cannot be equal to 2. Because if z were equal to 2, this output would be undefined, meaning that that's not going to be a point in our domain. So our inputs are points in R3 with the restrictions that x has to be greater than or equal to 0, and z cannot be equal to 2. The rules about the domain are going to be the same types of rules that you've seen in previous courses, where square roots are things to watch out for, denominators equal to 0 things to watch out for, and another thing is that natural logs also need to be positive. So any input into a natural log function would need to be a positive value, and that might cause a restriction as well. Let's look at a 2-variable multivariable function. So in this case, my inputs are just x and y, and my outputs is going to be x squared plus y squared plus 2. So notice that my output is just a single arithmetic output. It's not a point, it's not a vector, it's just some number. If I plug in an x and a y, it's going to give me out some point z. And let's explore what this looks like graphically. Graphically, I'm thinking of my x's and my y's as my input values, and my x squareds and my y squareds as my output values. So when I'm thinking about here's my x-axis, my y-axis, and my z-axis. I'm going to graph this in 3 dimensions. And so my input is an ordered pair, and my output is what I'm going to think of as my z value. So in this case, I'm going to let z be equal to f of x, y. So when I'm graphing this, the points on this graph are going to have coordinates x, y, z, and in this case my z is given by f of x, y. What do I mean? Let's go ahead and make a table that represents this. So if my input are ordered pairs x, y, and my outputs are z values, which in this case is f of x, y, if I have an input point of 0, 0, meaning my x is equal to 0 and my y is equal to 0, my output is going to be 0 squared plus 0 squared plus 2. It's going to be 2. So this corresponds to a point in 3-dimensional space given by the point 0, 0, 2. That's one point that lives on this graph. And I can continue doing this for other points that live on this graph. Let's say that I let my x equal 1, my y equal 0. What point does that give me for an output? That's going to be 1 squared plus 0 squared plus 2, which is equal to 3. So that gives me another point. This is the point 1, 0, 3. So I'm going to go 1 in the x direction, 0 in the y direction, and then 3 in the z direction. 1, 0, 3. And I can continue plotting this for a whole bunch of points. So my input of 2, 0 gives me an output of 2 squared plus 2, which is equal to 6. And that gives me a point 2, 0, 6. As you can see, it would be really tedious if I had to go about plotting every single point that lived on this function with this output space in 3-dimensional space. So we have a shortcut for doing this. And I'm going to tell you the first shortcut is to look at vertical traces. So the first vertical trace that I'm going to do is a vertical trace where y equals 0. I've already set it up by having y equals 0 over and over again. So the vertical trace where y equals 0. Spatially, I'm thinking about slicing 3-dimensional space along the plane where y is exactly equal to 0. It means that the x's could go out and the z's can go out, but the y's are going to live right here at 0. So I get a plane that comes out of the board at this weird angle where y equals 0. Algebraically, when I evaluate it, I think about this as f of x 0, plugging 0 in for y, but leaving x as a variable. I end up with x squared plus 0 squared plus 2. Meaning that in this case, my z component function, or the z values of the graph of this function, are going to be given by x squared plus 2, where y is always equal to 0. And we recognize this. This is just the graph of a parabola. This is a graph of the parabola along the plane where y equals 0. And so if I were to draw this out, I'm squishing the parabola because it's sort of tilted because it's in this plane where y is equal to 0. This is a vertical trace where y equals 0. It just gives me this one parabola. If I do a bunch of vertical traces where y is equal to a bunch of different values, then it'll trace out a bunch of different parabolas in this case. So I could look at where y was equal to 1. That would be given by f of x1, which is x squared plus 1 squared plus 2, which is another parabola. This time the intersection is going to be up a little higher, but be careful when drawing it. Keep in mind that this is the plane where y equals 1. So instead of looking at the plane where y equals 0, I'm shifting over to the plane where y equals 1, and the parabola moves up a little bit. So I have another parabola up here. And if I look at the trace where y equals 2, I get yet another parabola, and it's given by x squared plus 2 squared plus 2 is 6. Maybe I've already done this work. And so I'm looking at the plane here, the plane where y equals 2. I'm shifting over one more, and my parabola is up even higher. Sort of running out of room of where to draw pictures. So I have this sequence of parabolas. Just for the sake of completion, let's look at what happens when y equals -1. That means that I'm looking at the trace along the plane y equals -1, and the relationship between the x variable and the z variable is given by x squared plus -1 squared. -1 squared is +1, plus 2 is 3. So it means that when I'm looking back here at my negative y equals 1 plane, it'll also trace out a parabola. And now our picture looks terrible. We can't tell anything that's going on, right? So it gave us some idea, but smashing this into three-dimensional space, it's totally messy. I'm going to introduce it for notation's sake. If I wanted to, I could do a vertical